The creation of a Falcon 9 rocket begins long before any engine roars or any booster lifts off the ground. It starts with raw materials, specifically, a carefully engineered aluminum-lithium alloy that SpaceX uses for the main structure. These massive alloy plates arrive as thick, solid sheets that are inspected, heated, pressed, and rolled into long curved panels. These panels will later form the cylindrical sections of the rocket, but not before enduring an intense sequence of shaping and quality checks. Giant rollers bend the alloy into perfect curved arcs, while automated systems record every millimeter of deformation to ensure absolute structural precision. Once the cylindrical shapes are formed, friction stir welding, a key SpaceX technique, joins these panels together. A rotating tool generates heat without melting the metal, creating an incredibly strong bond. The process is slow, steady, and exact, fusing the alloy plates into a single seamless structure. Sparks glow around the tool as robotic systems monitor temperature, torque, and internal stress in real time. Next, these newly welded barrels are placed into large rotating frames where alignment lasers inspect circularity. Any deviation is corrected before assembly continues. Internal stiffeners are added, giving the rocket the strength needed to withstand the massive forces of launch and re-entry. By the end of this phase, the Falcon 9's outer skeleton begins to take shape, not yet a rocket, but a rigid, lightweight framework ready for tanks, engines, and avionics. This early stage lays the foundation for every mission to come, combining precision engineering with large-scale industrial power. At this stage, the Falcon 9 begins to transform from a hollow shell into a functional piece of aerospace hardware. The first stage, the largest and most powerful segment of the rocket, houses two massive tanks, one for RP-1, a refined kerosene fuel, and another for superchilled liquid oxygen. These tanks start as domed bulkheads, each formed from curved aluminum-lithium sections that are welded together using SpaceX's high-strength methods. Technicians inspect every seam using ultrasonics to verify structural integrity, since any flaw could compromise the entire mission. The cylindrical body is reinforced with long vertical stringers, installed inside the tanks to prevent buckling during ascent. Meanwhile, robotic arms weld the tank walls with millimeter-level accuracy. As the tanks grow in height, rotation platforms slowly spin the structure, allowing welders and robots to reach every angle without repositioning the entire assembly. Once completed, the tanks undergo stress testing, first with inert gases, then with cryogenic liquids that simulate real operating conditions. Engineers monitor temperature gradients, expansion rates, and pressure tolerances. Inside enormous assembly bays, technicians install internal plumbing that connects the two tanks to the 9 Merlin engines that will eventually sit at the base of the stage. Finally, precision-aligned mounting points are added, allowing the engines, avionics bays, and interstage connectors to attach securely. The first stage now resembles a massive, fully engineered fuel system, one designed to survive violent vibrations, rapid acceleration, and the extreme cold of spaceflight. Every detail completed in this phase ensures that the rocket's core is stable, efficient, and ready for the power it will soon unleash. The beating heart of the Falcon 9 is its Merlin engine, and building one requires a combination of metallurgy, precision machining, and high-pressure testing. Production begins with forging the turbopump housing, a component that handles enormous rotational speeds and pressures. Steel billets are heated until nearly molten, then compressed into shape under thousands of tons of force. After cooling, CNC machines carve out internal channels with microscopic accuracy, ensuring the pump can spin at more than 30,000 revolutions per minute. Injector plates, often called the engine's brains, are machined from solid metal blocks using ultrafine drills that create dozens of tiny fuel pathways. These channels must be perfectly sized to mix liquid oxygen and RP-1 in the exact proportions needed for clean combustion. The regenerative cooling channels inside the nozzle are welded layer by layer, forming a spiraling network that carries cryogenic fuel to cool the engine as it fires. As the engine takes shape, technicians assemble valves, sensors, and the combustion chamber. Once complete, each Merlin undergoes a violent ritual, the test fire. The engine is bolted to a stand, fueled, and ignited while engineers monitor pressure curves, exhaust signatures, and vibration levels. Flames shoot downward as the engine roars to life, producing thrust strong enough to lift a multi-story building. Only after passing all tests is the engine cleared for installation. When 9 Merlins come together, they form one of the most reliable rocket propulsion systems ever built. The next major step in building a Falcon 9 involves the structures that make reuse possible: the interstage, grid fins, and landing legs. The interstage begins as layers of carbon fiber fabric, each placed inside a large mold that gives it shape. These layers are coated in resin and cured inside an industrial autoclave, where heat and pressure bond them into a rigid composite cylinder. Lightweight yet incredibly strong, this component connects the first and second stages during flight. The grid fins, famous for guiding the booster during re-entry, are made of titanium, a metal capable of withstanding intense heating as the rocket plunges back through the atmosphere. CNC machines carve each fin from solid titanium billets, forming a complex lattice pattern. Engineers test their movement using hydraulic rigs that simulate aerodynamic forces. Meanwhile, the landing legs are built using aluminum and carbon fiber components. Assembly involves installing shock absorbers, hinge mechanisms, and locking systems that secure the legs during liftoff and release them during descent. These legs must deploy flawlessly to support the booster's weight upon landing. As these components come together, technicians integrate them onto the first stage. The interstage is bolted to the top, grid fins attached near the upper section, and landing legs fold neatly against the base. This phase transforms the booster from a simple propulsion system into a reusable vehicle designed to return safely after delivering its payload. The second stage of the Falcon 9 is smaller, lighter, and optimized for vacuum operation. Construction begins similarly to the first stage, with the rolling and welding of thin aluminum-lithium panels. But because the second stage operates beyond the atmosphere, density and weight reduction are even more critical. Engineers use thinner walls, tighter tolerances, and lighter internal structures. The Merlin vacuum engine, recognizable by its enormous nozzle, is assembled specifically for high-altitude performance. Its nozzle is made from niobium, a metal that can withstand extreme heat while remaining lightweight. The nozzle's large size increases efficiency in the vacuum of space, where exhaust gases expand freely. Technicians weld regenerative cooling channels along the nozzle's inner surface, ensuring it stays within safe temperature ranges during operation. Inside clean room facilities, avionics specialists install the electronic systems that guide the second stage through orbit insertion. Wiring bundles, sensors, navigation units, and computer modules are arranged with extreme care. Even small particles of dust could interfere with sensitive electronics, so technicians work under strict contamination control procedures. Finally, the engine mounts, fuel lines, and control systems are connected and tested. The completed second stage undergoes pressure and vibration tests to ensure it can survive both ascent and orbital operations. This lightweight yet powerful component is responsible for placing payloads precisely where they need to go. At this point, the Falcon 9 is nearly complete, but several critical systems remain. One of them is the payload fairing, a protective shell made from carbon fiber composites. Technicians lay multiple layers of carbon fabric onto large molds, infuse them with resin, and cure them in massive autoclaves. The result is a lightweight yet incredibly strong structure designed to shield satellites during ascent. Inside cleanroom environments, engineers assemble avionics modules that will control the rocket throughout its mission. These include flight computers, navigation sensors, communication systems, and wiring harnesses. Every cable must be routed with precision to avoid electromagnetic interference and ensure redundancy. As final integration begins, the first stage, second stage, and interstage are stacked together inside the assembly building. Cranes lift each section into place while technicians align mounting points with millimeter accuracy. Additional sensors, plumbing, and external panels are added as systems come online. This phase marks the moment when the Falcon 9 becomes a single unified rocket, an engineered machine ready for transport to the launch pad. The nearly finished Falcon 9 now begins its journey from factory to launch site. The rocket is carefully lowered onto a specialized transporter and moved horizontally through roads and highways, accompanied by escort vehicles. Once at the launch facility, technicians transfer the rocket to the transporter erector, a massive structure that carries the vehicle to the pad. Hydraulic actuators slowly raise the Falcon 9 into its vertical launch position. With the rocket secured, ground crews begin a series of final tests. Fueling pipes are connected, liquid oxygen and RP-1 lines are checked, and electrical systems are verified. Before any mission, the Falcon 9 undergoes a static fire test. The engines ignite briefly while the rocket is held down by the pad clamps, producing a thunderous plume of exhaust. Engineers analyze data from sensors embedded throughout the rocket to ensure every component behaves as expected. Final inspections follow, including pressure testing, avionics checks, and a complete review of the rocket's telemetry. The Falcon 9 stands tall, fully fueled, and ready for its mission. Soon, the countdown will begin and the vehicle will rise from the pad, carrying satellites, cargo, or astronauts toward orbit. Everything built throughout the manufacturing process converges in this moment.